3, 2, 1. Hello everyone, welcome back to week 4 of Intro2Astro 2022. Thanks a lot for joining us today. I know it's a Tuesday instead of a Monday. It's great to see many of you today. We will recreate the discovery of transiting planets today using the NASA TESS mission. And we will also discuss both LaTeX and Overleaf, both of which are great tools that can help us write scientific papers. And we will hear from Priya about her life story as an astronomy faculty member. Meanwhile, feel free to send us any questions or feedback both here on YouTube and on piazza.com. All right, let's move on to the first topic today, the transiting exoplanet and the NASA TESS mission. And the floor is yours, Sam.
All right, let me just share my screen. All right, so today we'll be talking about finding exoplanets with TESS. And so my name is Sam Yee, and I'm currently a graduate student at Vincent. And yeah, my area of research is quite closely linked to the TESS mission. And so I'm really happy to be able to tell you about how you can use, how we are using TESS to find and study exoplanets. So just to recap, what is TESS? TESS is the Transiting Exoplanet Survey Satellite. And as the name implies, it searches for planets using the transit method. And so if you remember from the overview of exoplanets from a couple of weeks ago, detecting exoplanets through the transit method relies on the alignment of the planet passing in front of its host star, and that causes a tiny dip in brightness, which if you can measure the brightness of a star very precisely and you see these periodic dips in brightness, it tells you that there could be a planet going around the star. And so just to give a rough sense of how large the changes in brightness are, for a Jupiter-sized planet, it would cause a roughly 1% change in brightness. So the brightness of the star, of a sun-like star, would dip by 1%. And for an Earth-like planet, it would be 100 times smaller than that. So it would be 1% of 1% of a change in brightness. And as you can imagine, this is a pretty difficult thing to do, but it can be done, and in fact has been done for a long time, for more than 20 years, in fact. And the early exoplanets surveys from the ground were mostly transit-based, and two of the most successful exoplanet surveys from the ground have been WASP and HATNet, and both of these have discovered roughly around 100 to 200 planets each. But one of the problems with trying to search for transits from the ground is that the atmosphere gets in the way. And that's a big problem, because if you've ever looked at the sky, you'll know that the stars twinkle, and that's because of various atmospheric effects, where you have turbulence in the air that changes the brightness of the stars independent of the stars themselves. So it's purely things that happen on Earth that change the brightness of the star. And so if you really want to search for small planets or planets around fainter stars, then you kind of have to get above the atmosphere. Otherwise, the noise that's caused by all the atmospheric turbulence, even on the best observatories on Earth, will just swamp out the signal completely. And so by far the most successful exoplanet hunting mission to date, at least, was the Kepler mission, and Kepler discovered more than 2,500 confirmed planets. That doesn't even include the planets that were found by the K2 mission, which was basically what Kepler was repurposed into after the failure of its reaction wheels. And so Kepler was a roughly 1 meter diameter telescope and was able to detect very small changes in brightness, as small as you would need to detect an Earth-like planet going around a sun-like star. So the precision of Kepler was on the order of 1% of 1%, which is amazing. And you would not be able to do that from the ground. Unfortunately, Kepler didn't last forever. And so after about 8 to 9 years in space, it ended its mission. And today we have TESS. And TESS is a really great successor to Kepler because it's not just the same thing as Kepler, but it does something very different. And as you can see from the cartoon on the screen, TESS actually has 4 separate cameras, and each of these 4 cameras looks at a different part of the sky. And over the course of its 2-year mission, the field of view of TESS rotates, and so over the course of 2 years, it actually observes the entire sky. And TESS was launched in 2018, and so it's really been observing for almost 4 years, which means that it's observed most of the sky twice already. And so here in this picture, you can see the different sectors that are observed at any given time, and the spacecraft rotates its field of view so that over the course of 2 years, it observes the entire sky. All right, so that's the brief overview of what TESS is and how it searches for planets. Now let's dig into the data and see how you too can find a planet. All right, so this Jupyter notebook is on the course's GitHub page, so you can take a look later on. And so what we'll be doing is we'll be using this Python package called Lightkuve, which is developed by people at NASA to help us to be able to download and to be able to analyze the light curves from TESS. And so if you go to the Lightkuve page, here it's spelled with a K, so Lightkuve, you will be able to see more tutorials and all the documentation that you might need to understand how to use it. But today I'm just going to give you a brief overview of how we might do it. So as I mentioned, TESS observes each sector of the sky for 27 days at a time and monitors the stars in the sky for those changes in brightness. And after the 27 days has passed, it downloads the data to Earth, and pretty soon after, just a few weeks later, it's already available publicly. And so that's, I think, one of the most remarkable aspects of the TESS mission is that all of the data is publicly available, which means anyone can access it. And so we'll use Lightkuve to download and look at some of this data. And in particular, we'll be searching for and recovering TESS's first exoplanet, Pi Mensae C, which was published in 2018. So to do this, you'll need to install the Lightkuve package, and I included the code that you would need to install it here. You can just run it in the Jupyter notebook, or if you run it in your terminal window, you'll just remove the exclamation mark in front. But because I've already installed it, I'm not going to run that cell. Instead, we'll start by importing all the packages we need. So these are just NumPy, Matplotlib that you've seen before, as well as Lightkuve, which I've imported as LK. So the first step to be able to look at some of the TESS data is to search for it and download it. So Lightkuve has a very convenient search function. It's just search_Lightkuve, and you can give it the name of the star. So not all stars have names, of course, and you can instead give it the ID and the TESS input catalog. So Pi Mensae is also known as tick 2611366679, and so you can search for any star that way. I've selected to download the TESS data, and in fact, Lightkuve lets you download data from Kepler as well. And in this particular case, I've also selected the author to be Spock, which is the TESS Science Processing Operations Center. And so basically, there are various pipelines that have processed the TESS data, and you can find all of them online. But today, we'll just focus on the Spock pipeline, which is, the official NASA pipeline to download the data. So if you just run this cell and you look at the search results, it'll take a couple of seconds to do the query, but you'll find a whole list of the data products. And so Pi Mensae has been observed actually in multiple sectors of TESS. So if you remember the diagram of what the different TESS sectors look like, some of them overlap. So Pi Mensae is in one of these overlapping regions, and it was observed in sector 1, 4, 8, 11, 12, 13, etc. And it's also a star that was observed with a 2-minute cadence. So the exposure time column here says 120 seconds. But also, in fact, in the extended mission of the TESS, so after the first 2 years, it was also selected for 20-second cadence observations. And so you can see that in sector 27, this star was observed with a 20-second cadence. So you can see there's tons of data available for this star. But for today, we'll just focus on looking at the sector 1 data, which is what they used to discover the planet. So how do we download it? So if you only want to download the first row, which corresponds to sector 1's data, you'll see that the first index is 0. And so if you go to search underscore result 0, and then you type .download, it downloads the Lightkuve. And we can plot this data just by typing lc.scatter or lc.plot, and you can see the data here. So it's kind of messy, the data. These are all of each point is, there's a point every 2 minutes, and so it's a pretty noisy Lightkuve. But even by eye, because this is such a bright star, you can actually kind of see the transits already. I don't know if many of you will be able to spot them, but you'll see a tiny dip in brightness here. There's another tiny dip in brightness here. And so these are actually the planets' transits. But as you can see, there's also tons of other random things that happen. So there's a gap in the data here, and that's because in the middle of every sector, TESS downlinks part of its data to the Earth, and after that, it needs time to be able to point back to where it's looking. And so there's a gap in data, and the data right after this gap is kind of wonky. There's some weird stuff going on here that actually is because of some pointing issues that the spacecraft had. Remember, this was the first sector of the mission, and so there are plenty of bugs to be ironed out. And there's also some very tiny dips here, like for instance, this one, that might trick you into thinking there's a transit, but it may not necessarily be. In fact, this particular dip here is actually just some issue of the spacecraft. So if you want to actually search this Lightkuve for planetary transits, we'll have to do some cleaning. Unfortunately, part of that cleaning of the data has really been done for us. So in this particular case, the Lightkuve I'm showing you is known as the simple aperture photometry column. And so that's just taken by taking the star's brightness and just plotting it over time. So it's not corrected for anything. But the Spock Lightkuve, so the Lightkuves that were produced by NASA, have also another column, which is the PDC SAP flux. And that stands for Pre-Search Data Conditioning, where they've tried to correct the Lightkuves of some of the systematics that occur with the spacecraft. So if you type lc.select_flux and you select that column instead of the SAP flux column, and you plot it, now you see it's a lot cleaner. So you can see the transits a lot more clearly, but all of the very large systematics are gone. For instance, this huge ramp here that occurred just after the data downlink, it's been corrected off because that's really just a function of the spacecraft. And because we know what the spacecraft is doing at any given time, we can try to correct for those effects. There's still a bunch of other effects. You can see a slight modulation in this Lightkuve. So for best results, I would suggest cleaning this data again. Unfortunately, Lightkuve also has a flatten function, which basically runs a high-pass filter to remove any low-level trends. So I've done that here. So I type lc.flatten, given it a window length, which is here it's 501 pixels. So it's basically 1,000 minutes. That's the kind of the where this frequency at which the signals will be filtered out. And I've also typed this .remove outliers just to remove any random outliers that may occur in the Lightkuve. And so if you run that and you plot that again, now you see some of these weird curves in the Lightkuve have been flattened out, but it didn't really do much else. And that's because this Lightkuve is really pretty clean. Okay, so now we have a clean Lightkuve. You can kind of see the transits, and we know now at least they're not from spacecraft systematics. So how do we find the transits? If you're given this Lightkuve, sure, you can see it by eye, but that's not super scientific. So how might we actually go about finding the transits? So the most common method used to find planetary transits and Lightkuves is an algorithm that was developed in 2002 called the box least squares algorithm, and basically tries to fit a box shape for the transit. And it searches many different periods to find the best period where you could possibly have a transit event. And again, Lightkuve has a very convenient built-in function to perform this search, and it basically produces a periodogram, which is similar to a Fourier spectrum. So here I just type lc.2_periodogram, and I use BLS, which stands for the box least squares, and I can plot that periodogram. And so what you see here is a plot of BLS power against the period. So basically what the algorithm is doing is that it's taking all of these different possible planet periods or transit event periods and it's searching for whether there is a transit at that period. And if there is, then there will be a good match, and the higher this peak, the stronger the match is to the transit. So as you can see here, there's a very strong peak at just over 6 days. And we can see what that period is by typing BLS the period underscore at max power. So this is the maximum, the peak with the maximum power. And we can also find the transit time of it. So now that we have period, what we can do is that we can look at the light curve with our own eyes again to see if it's a real signal. So to that, we fold the light curve on that period, and that means we repeat the time series every p days, where p is the period. And again, light curve has a function to do that, where it's lc.fold, and you have to give it the period and the time at which the transit occurs. And so I generate the folded light curve, and if we plot that, it's taking a moment because I'm also binning the light curve, so to make it easier to see the transit. Yeah, and so this is basically the same light curve, but now what I've done is I've taken all of these transit events and folded them on top of each other. And so that helps to build up the signal to noise as well. And so in gray, I've shown all of the individual points. Remember, these are all taken at every 2 minutes. And in red, I've binned the data so that now there's one red point every 30 minutes. And you can see a beautiful transit here. It has the shape that you expect from a planetary transit. And yeah, this is basically the transit that represents the very first planet that TESS discovered. So we can just check to see if the transit occurred, if what we found is the real planet that this paper by Chelsea Huang et al. Found, and they found a period of 6.27 days, which is basically the same as what we found. And of course, if you actually want to analyze and characterize the system, and what this paper did was to do a more detailed analysis of the system. They got more observations, so they got radial velocities or high resolution spectra of the star, but they also fit all of the data together. And so you can also do that with a code like Batman, which helps to fit the transit event, or exoplanet, which lets you fit transit events and radial velocity data. But that we'll hear about some of these other codes later on, but we're not going to do that today. What we've done is we've already been able to find the planet. And just as a little bonus, Lightkuve also has a very convenient interactive box least square algorithm where it actually makes all of the plots I just showed you at once, and you can kind of zoom into the data, and you can see the transit here. So the model isn't very good, but you can still see the data in black at the back, and you can see the same transit event that we found. And if you click this, if you click a different peak, it will recalculate everything, and it will fold the data on that new period to see, so that you can see if that's actually a real transit event or just some issue with the data, or in this particular case, actually what these different peaks represent are actually aliases of the transit event. Okay, it's supposed to select this if you click it, but I guess it's not working on my computer, but you should give it a shot. And one of the assignments I put at the end of this document was to try to search for planets in multi-planet systems. And so I think this is particularly useful when you have many different periods that you might want to investigate. So the last thing we're going to look at today is to look at the TESS objects of interest list. And that's because if you don't want to search for transit candidates itself, you don't have to worry, because the TESS team has already done it for you, and they've already searched all of these light curves and vetted all of the transit candidates. And so they've published a list of TESS objects of interest, and you can find that at this link that I've provided. And you can see there are almost 6,000 test objects of interest currently available. And you can download this entire table. This table gives you a ton of information about each transit event and the star that it orbits. For instance, TOI-101, which is the first TOI that was flagged by the pipeline. It says here it's a known planet, so it was previously known before TESS. And if you scroll to the right, there's a ton of data in this column, and you can see that it's actually WASP 46b, so it's known before TESS. You can also see what kind of star it orbits. So it orbits a star that's quite similar to our sun with an effective temperature of 5,600 Kelvin, and it's about 400 parsecs away. So there's a lot of data here to play with, and you can download the entire table just by clicking download table, and you can download all of the rows or some subset of them. You can also download them directly using pandas. So here I've actually typed in the URL of the data website, and I can just read the data directly from that website and look at it. So it's going to take a minute to download the data. I guess the website is being a little bit slow today. But yeah, so also on this website, since we're waiting, there's a ton of other information that you can look at. For instance, I think Pi Mensae is TOI 144, and if you click on this link, it will actually bring you to a new page that actually gives you a ton of other information about it. For example, other observations that other people have made that you can see at the bottom. So people have taken various spectroscopic observations of this, and so on. All right, so the data is downloaded. So again, here I'm showing just the first 5 rows of that table that's on their website. But now that I've got it into Python, into a Python notebook, you can do all kinds of interesting things with it. You can look at how the different TOIs are distributed. And so here I've now plot all of the test objects of interest as a function of the orbital period on the x-axis and the planet radius in Earth radii on the y-axis. And so you can see that most of the planet candidates that TESS has found have orbital periods of about less than 30 days. And that's because TESS observes each sector for only 27 days. So it's very difficult for TESS to be able to find planets that have longer orbital periods. Most of these planets will be in those areas where the sectors overlap. And also there's a ton of planets that are up here, which are bigger and so cause larger signals. There are a bunch of planets down here, and if you might remember from your reading last week, these objects between 2 and 4 radii are basically super Earths or sub-Neptunes, as we will call them today. And the ones up here are basically hot Jupiters. And the reason why there's so many more up here is just because they're easier to find. Hot Jupiters are actually very rare. They occur around only 1% of sun-like stars or less, but because the signal that they provide is like 100 times bigger than for an Earth-like planet, it's just so much easier to find them. All right, so now I think I've given a good introduction to TESS and how you can use the TESS data to search for planets yourself. And so I left a couple of additional assignments here, and so you might want to try them out. And there's also a ton of other resources on the Lightkuve documentation page.
All right, thank you so much, Sam. There was some beautiful light curves we have there. Right, our next speaker today is Maria, who's gonna show us how to write scientific papers with LaTeX and the overleaf. Take it away, Mary.
Okay, hi. I think you can see and hear me.
Yeah, we can hear you.
All right, so let me see. Let me share my screen real quick. Okay, so as Faye mentioned, today we'll be talking about overleaf and LaTeX. You've probably heard these two words being thrown around a lot. And so it's time that you all know what it means and why it's very important to astronomers. Okay, so what is overleaf? And when I had to answer this question, I realized let's just look at what Wikipedia has to say. So as it's given here, overleaf is a collaborative cloud-based LaTeX editor used for writing, editing, and publishing scientific documents. It partners with a wide range of scientific publishers to provide official journal LaTeX templates and direct submission links. So if you notice, I have underlined a bunch of words over here because those are the most important keywords to define overleaf. So overleaf is basically like Google Docs, except it's not in a regular word processing format. It's in this thing called LaTeX. And it is very important because it makes writing scientific papers so much easier because it gives you a wide array of templates for journal articles or your research reports or for resumes, things like that. And also, if you had to submit these articles somewhere to a recognized journal, they usually have direct submission links, which makes the process so much smoother than actually having to fill a physical form and then uploading everything. So I mentioned overleaf is like Google Docs and LaTeX. So the next question you would have in mind is, what is LaTeX? It's basically it is a software. It's not exactly a traditional word processor. You have to use plain text following a certain syntax, so like HTML or CSS. And the best part of LaTeX is it produces what you tell it to produce. You put in text, images, you format the text, you format the images, you put in other features, you tell it exactly where to place what, and it does that for you. So I mentioned here that you use plain text following a certain syntax like a markup language. A markup language is like HTML, where you enclose content in tags. So you would have tags telling that, oh, this is the document part, this is the actual part of the document. Or tags to show like this text is in bold, or this text is italicized, or this text has to be aligned a certain way, or this image has to belong on this part of the page. So unlike in a word processor where you simply type, drag, drop, click around, in LaTeX you literally type it and tell the software what to do and how exactly you want your finished document to look like. There are pros and cons to using LaTeX, which you should know before jumping into this. One of the biggest advantages for me, and I'm sure everyone here will agree to this, equations and inline symbols look great in the typeset results. So typically, if you want to type equations in Word or in Google Docs or in Pages on Apple, you have to go to the insert form. You have to go and insert these equations or the inline symbols from a different keyboard. You have to know what the options are. There are keyboard shortcuts, but it is a little cumbersome. You can't just directly type it in. But with LaTeX, using the right commands, which I will show you shortly, you can actually just simply type it in, and it looks like it's just a part of your regular text and not something that you've added on top of it. In Word and in Pages, I know when you add equations, they look a little different, and they look like images. You can't simply just copy and paste them like you do with text, but in LaTeX you can. That's a big advantage. Another advantage is once you type up your code or your template for a certain document, you can always reuse it. Maybe it can be for an entire document, maybe it can be just for writing equations or printing tables, but you can keep on reusing it because especially on Overleaf, it allows you to save something as a style file, and you can implement that across all the documents you write. It is possible to do this on Pages and on Word as well, but that's more of a page styling thing rather than a text styling or text formatting thing. In LaTeX, it allows you to format text and save that as a template. And last but not the least, well, there are several more pros. These are the three most important ones. But the third one is it's easy. It's an easier option to cross-reference and for bibliography. So when you're citing things, either in your image captions or in your main text, you can just you can just do /cite and a tag by which and it calls up whatever resource or article or website that you're supposed to be citing there. How referencing works, I won't be talking about in this little tutorial, but I have some resources linked at the end, and that should give you further understanding. Basically, you can create a separate document that lists all your articles and papers that you're referencing, and then you can call that in later in your main document. So LaTeX sounds great. It has all these pros, but it also has its own disadvantage. One, as you may have figured out by now, it works very differently from a conventional word processing software. So you have to do a bunch of work in the background to actually learn how to use it. It takes a little bit of time. You need to be patient. It is a very steep learning curve. So learning how to use LaTeX is time consuming and may not be the best option if you're going to use it just once in your life. But since you're all here to be astronomers or something related, it is worth your time. Two, tables are not easy to design. So in a word processing software or in like in MS Word or Pages or Google Docs, you can just go insert table and define how many rows and columns you want, and then you can just right click, add more, or use your shortcuts or whatever. But here you have to use separate commands for inserting a new row. You need to have formatting commands to show where on the page your table should go. It's a little harder. It's a little cumbersome to manage. You need to define separate formatting options to wrap text to keep, if you want to maintain your cells in a certain length. It does not come very naturally. It's not very intuitive always. And sometimes it's kind of like Python, where you have to import packages to use certain features. So sometimes it can be frustrating to find the right packages and to even get the basic things right. Sometimes you're missing a package which you didn't realize you were missing. Or maybe you have the package, but you haven't called the right formatting options from it. So, and you're not using it right. So all these things make LaTeX a little cumbersome to use. But if you take the time and if you learn it and you have the right resources at hand, it's actually worth it. So that's why. And so now let's say you're going to use LaTeX. Overleaf is not the only text editor. LaTeX and TESS, they're basically the same thing. TESS is basically how it was introduced. LaTeX is like TESS version 2.0, if you may. There are subtle differences between the two, but I'm not going to get into that now. So there are text editors that you can easily download on your desktop and you can work on it offline. Overleaf is an online option. But why would you want to use Overleaf? Because Overleaf is a much, much simpler LaTeX editor option, in short. It not only allows you to write things so in a regular text editor, you have to write everything like you're writing an HTML document, following that syntax that I told you about. But in Overleaf, if you don't know the LaTeX syntax, you can actually write things as a rich text editor, like as though you're formatting things on Word or Google Docs. And everything still works the same, even if you don't know the LaTeX syntax. You will still see this, and just as in a regular text editor, you will still see the typeset document that's being created as you edit your main document or you type it up. But the typeset document, I mean like the PDF output or however you want to save the output as. So now how to use Overleaf? It's very simple. You go to overleaf.com and if you already have an account, you just straight away log in. If not, you can start up with an account. You can register using your email address or using Google or using your ORCID ID. It's something people typically have when they're writing papers. It's kind of like, how do I describe it? It's kind of like your ID number, but for a world of scientific publishing. It's this unique number that's assigned to you as an author. So when people click that number on papers, they get to access and see everything and anything you've published. And Overleaf can also be connected to your GitHub. So especially if you're using Overleaf to write documentation for code or writing papers or research reports based on the code that you have on GitHub, I think it's a very useful tool. And also some institutions have a premium Overleaf service. So if your institution does, you should find that out. And because premium Overleaf has so many more features, which makes it wonderful. So once you log in, this is what your Overleaf screen looks like. For those of you who used it before, please be aware Overleaf has come recently with some more updates. So it looks a little different than it did maybe 2 months ago. So this was a screenshot of LaTeX that I took quite some time ago. This is what it looks like. And you basically click on new project if you want to create a new project. And you have all these bunch of options. You can create a blank project. You can, as I said, if you have something on GitHub, you can import it here. Like usually when you host code on GitHub, you have to create a markdown document. And so you can maybe import that and format it and make it look better on Overleaf. Or you could use anything from these bunch of templates they give. I cannot stress this enough when I say templates are basically your best friend in Overleaf. this option right here, it has a gallery of templates you could use. These are created for free use. They're created by people who use Overleaf all around the world. It can be, you have publishers, scientific journal publishers who have templates on here. And you also have people who created templates for things like a science presentation, a conference poster, maybe how to write a final exam, or maybe you want to write your CV, or maybe you want to write your thesis for college. You have templates for all of that. And so you should always use these templates, or else if you're interested in creating a brand new template of your own, feel free to do that. But for me, I always straight away go to these templates, or you could see I've created a bunch of files. So I just open one of those files and use that as a template for my next file. So once you create a new document, this is what it kind of looks like. This is a simple simple document that I've created just to highlight what the features of an overleaf window are. So this is the layout of your overleaf window. So I'm just going to go one by one through the main features here. So over here, so on the left-hand side, you have this panel that has menu-like options. One important one at the bottom is the file outline. So it basically gives you the structure of the document based on whatever sections and subsection headings you've used. So you can see in my main document screen. So this is, by the way, the format of how a LaTeX document looks like, the syntax that I told you about. I'll be exploring this further very soon. So you can see I have a section title saying introduction, another section saying pros and cons, another subsection saying pros. So it just gives that as a file outline just for a person to have a quick view of what your file looks like. And a lot of times, documents created here, when you download it as a PDF and you open it with a PDF viewer, you will see the same file outline if you choose to see it in the PDF viewer. The next important part is creating and uploading a new file to create and upload files and to manage these files. So now an overleaf document is not necessarily just one main text file. Main.text is basically where you write it's a conventional name for the main text document where you write up all your information that you want to be printed. But you also have other supporting files. You could have a couple of you could have all the images that you need to put in your LaTeX document. You could have style files, so markdown.sty. Sty is a style file, which basically is a pre-created document that tells what formatting you need to do for this document. Then refs.bib. .bib is basically for bibliography. I don't really use it on this document, but it's very handy. And on the top, you can see you have options to create or upload new files or folders or to delete them. And you can upload files either from your computer or you can just pull them in from other overleaf files. Sort of like how in Google Docs, where you can either upload things from your computer or upload things from your drive. The next thing over here, I've shown you before, source versus rich text. You can either type it like this, as I've shown here, or you can switch to the rich text format if that's more comfortable. Although I would suggest learning this format because it's so much easier and you feel like you're in control. Now, this symbol right here is, you could actually click and choose special symbols instead of directly typing them in. So for example, if you want to print the symbol for alpha, you have to do $, $/alpha, like spell it out, and then $, again. But if you don't want to do that, you can directly insert it from there. But I've started it because it's a premium feature. So if you're a free user, like most of us, you have to type it in. Then review right here tracks edits. Now that is also a premium feature. So that basically works as tracking or reviewing changes like you have in Google Docs or in Microsoft Word, and it's very useful if you're working with a collaborator. Share lets you to share with a co-author. So in a free version, you can share with one more person. If you have a premium account, you can share with multiple co-authors, and it's very helpful when you're writing an article to be published, because usually you would be collaborating with multiple people on a project. And submit here is usually for journal submission. If you're using a template for a journal, let's say you're using an AppJ template, you would directly have a submission link for AAS. So that it is a little more fast track than actually having to upload your document, because even for the reviewers, it's easier to manage this. History here shows you the changes you've made in the document, you or your collaborators have made in the document over the last 24 hours. If you want all of the history ever since the document was made, again, you'll need a premium account. Now, this is a new option, layout, that manages the layout of this window. This is the standard layout, but you could also manually adjust it by, like, you can see there's a border separating the PDF version and the text version. So you can just drag around, click and drag to manually adjust the layout, or else you could go to layout options, layout menu right here for some preset options. Chat is to chat with your co-authors, just like you do in Google Docs. And this little sign right here is to download the PDF version of what you've just printed. The little text paper right there, that symbol is to switch between your output file and LaTeX log. So right here on the right-hand side is the output file or the typeset file. But if you have any problems that is preventing you from getting an output, you may want to switch to the LaTeX log for debugging. So it just works like Python or any programming language where the IDE or the code developing environment would give you an option to debug your code. That is your debugger in LaTeX. And then recompile, it basically is to compile your changes. You could either have that happen automatically, so each time you make a change, it's synchronously updating your PDF document. Now that could be a little memory consuming and a little cumbersome, especially if there are a lot of people who are on a LaTeX server at a given time. Or you could compile manually, that you make a bunch of changes and then compile it. Then you compile it after a while. And then you have an option to compile it with or without images. Again, depending on the bandwidth you're on, you want to make a choice. Now, this is the main thing. I skipped the menu option because it has a lot, and this is basically what menu looks like. I just made it 3 panes, but it's actually a single pane that is scrollable, but I just made it for you to just view it better. So in the menu, you can choose to download your files, you could do a main account, you could sync it with your GitHub, your Dropbox, and all of that. You could change how you view the document. So this is how its standard looks. This is its standard appearance, but you could have it have a dark theme. You could change the font. You could change the font of the typeset of the code document. You could change how things look like. You also have a help option if you get stuck with all of this. So these are the main features of LaTeX and how, not LaTeX, of Overleaf, and how to navigate yourself around a document. Now, going into the basic LaTeX template that I created. So this on the left is what I typed. On the right is the output, what I get from whatever I typed. Now to break it down as to what is in here. Every LaTeX document has 2 parts, 2 main parts, a preamble and the document environment. Now the preamble is basically that part like in Python where you import all your packages. You define the type of document you want to create. So document class article is usually the standard, but you have other document classes. Or if you're using a journal template, you want to call that template. For that, you would have an additional file, but that's another thing, so I'm not going to cover that for now. You're going to define a document type, and you're going to import all the packages that you need by calling /use package. And then after the preamble, you have your document environment. Basically, it is the actual content of your document that needs to be displayed, including all the markup type commands. So, your bold, italics, underline, inserting images, inserting equations and tables, that sort of thing. Now, the document also contains your other pages like your bibliography, index, glossary. Those things, they need not be included physically in the document environment. You can create it in other text files, and within the document environment, you can call it. I won't be covering that now because that's a little too advanced for this session, but you have resources where you can look it up. And the preamble, there are these 2 things that I want to point you to do. The package, which is basically what you call. So let's say when you're doing import numpy. Numpy is your package, and that's what it's called, package in LaTeX as well. But before certain packages, you see something in square brackets. Now, those are keyword arguments that override default settings. Some packages are set in a certain way, but then, so it's kind of like functions in Python. if you call a function, you will want to define some keyword arguments. Some functions have default arguments. So if you just call the function without those arguments, it's going to behave as it's set to do in default. But you could override the default settings by using these keyword arguments. Now, this was the main document. If you see towards your bottom left, you can see something I wrote as begin figure and end figure. Now, this is creating your figure and figure environment. So right here, to create a figure or a figure environment, you need your image package. Use package GraphicX. GraphicX is your go-to image package. It pretty much works like Pylab or Matplotlib in Python. Now, you want to create a figure, so you can either insert a figure with or without the environment. We always want to do it with the environment because it comes with additional features. So begin and end creates a new environment. It can be a new environment for figures, a new environment for tables, a new environment for lists, a new environment for equations, etc. Here, we define begin figure and end figures, so we're creating a new environment for a figure. Include graphics is basically what inserts the image. So include graphics and the option curly brackets, that calls your image. Now, how does it know which image I'm talking about? If you saw earlier, a couple slides back, in the file on your left-hand side pane, you could upload your image from wherever it's saved, and when you're calling it, Overleaf knows that you're calling an image from this. And whenever you're inserting an image or something external, it always has to be in the same Overleaf file that you're writing your main document in. So include graphics actually includes the image. And if you want to, change its size or crop it, you would want to insert the keyword arguments in square brackets right after you write include graphics. Caption here gives you the figure caption, and it automatically numbers the figure caption for you. So it is so easy to manage. Label here is kind of like a tag. So when you're writing the document, for instance, I want to say figure 1 shows the logo of LaTeX. So instead of writing figure 1, I can always call this image by saying /ref and the /ref and the tag. So here I call it as fig latex fig. So I can call it as /ref fig latex fig, and it automatically puts in the words figure 1 for me. And if you enable it, that actually becomes a clickable link, which lets you jump directly to that image. Now that's all about figures. Now for math, which is the most interesting and easy part of LaTeX, you could either have math inline or you could create a separate equation line. So if you're creating an inline math option, I just put this here. This is literally what you type. You can type whatever words you want, and whatever math you require, you put it between these two $signs. Or if you want to create a separate equation, you create an equation environment by saying begin equation, end equation, and within that you enclose everything you want, and this time you don't need your $signs. An equation environment, just like an image environment, it gives a little number, the equation number there, and you can also add label here, so you can give your equation a name. So let's say, I forgot what this equation was for. It was I just remember it was from some aspect of statistics, astronomy statistics, I think the T factor or something like that. So I can call it label T, I can put the label as T factor and then ref T factor, and it will give me the equation number 32. So as I said, $sign is used for equations, mathematical, and other special symbols. Now, if you see I've written things like an underscore and /frac or a caret sign, now those are for placement. An underscore means subscript, a caret sign means superscript, which is pretty standard across all text editors. And to insert things like a square root symbol or make things look like an up and down fraction, I insert these words. And this equation number I said is inserted by the equation environment. Now for table. Again, for a table, you still need to create a table environment. But if you can see that it has something called begin table and begin tabular. Now begin tabular is the thing that actually creates a table. Begin table, it lets you put in the other supporting information you need for the table. So if you compare it to our image thing, begin tabular and end tabular is basically the include graphics part of it. Begin table and end table is basically where I put in my captions and labels, etc. And the two things that you need to know here, or three things you need to know here, are how to insert the new row and how to manage the number of columns. To manage the number of columns, we define this little curly bracket thing right after begin tabular. You basically put in these bunch of letters to define how many columns you want, but these letters determine either the size of your column or the alignment. So I put in CCC, which means I want 3 columns where everything is center aligned. If I put LLL, I would have 3 columns with everything left aligned. And if I want lines between my columns, I put in these vertical lines here. If I don't want borders between each column, I simply put CCC and it works out. Or if I just want a border on the exterior of the table, I put line, CCC, line. The double slash here is to insert a new line. It works not only for tables, but also works in the main document. And /H line inserts a horizontal line. Again, it works everywhere and not just in the table. So that's what I have. These are some useful LaTeX resources compiled by NYU Libraries and Harvard Library. This is uploaded as a PDF on the GitHub, so these are clickable links. And for Overleaf resources, the best one is to go to Overleaf's official tutorials, because they break down everything so beautifully and enables you to use Overleaf very efficiently. And as for your assignment, it's very simple. And so there won't be a solution key, because obviously it's going to differ from person to person, but obviously feel free to ask any of us on Piazza. You basically pick up a topic in astronomy of your choice, and using the AppJ template in Overleaf, you now know how to search for templates. You write a 2-page paper on the topic and you create separate sections on it. You saw how I did that. You just do section, you can create a section, or you can create subsections if you want those. So you create a topic paper with these few sections, and just to get a practice with it, you can include a few images, few occasions, and at least one table. And an extra thing that I did not cover here is to type in references or using a .zip file. The reason I didn't cover this here is so that to give you a motivation to actually go over these resources. That's my time, and this is all I have to say. If you have any questions, you know where to ask, and I hope you got something out of it.
Thank you so much, Maria. That was really informative. All right, let's move on to the final speaker today. Oh, by the way, we are skipping the reading assignment topic today because our speaker, Namisha, was not feeling well today. Yeah, let's move on to our final speaker, Priya.
Thanks, Faye. And hello, everyone. I'm Priya, and I'll be talking about the story of my life. And I want to say I really enjoyed hearing Tim's story, which was really, so colorful. It had so many aspects to it. Mine is a rather direct story in the sense it was early, probably I was barely 12 or 13 by the time I already knew I wanted to do astronomy. And that was probably because of, I grew up in the city of Bombay, which is in India. And we had a planetarium and some amount of public outreach, which was done by astronomers in the city when they visited or, on regular basis. And that's also the time when Carl Sagan's Cosmos was aired on television. And that's when I think I went totally head on for it, because I just loved the series, as well as my father bought me the book. So there was lots more in the book. And that is why I even to now, I very strongly believe that public outreach is very, very important, because a lot of children, a lot of students do not know of the possibility of, for example, taking up astronomy as a career. Most little kids want to become astronauts, but the idea of actually doing astronomy as astrophysics, as a science, many of them do not even know that this is possible, and how do they actually go about it, or what are the things that they would study if they do it. And that's why even now I'm very active in public outreach and education, because I think that's a very important aspect, and actually as bringing us young blood, new people into the subject, basically just by exposure. And a long time back, I actually thought that it was actually making everybody an astronomer. But now I very strongly believe that it needn't be done with the idea of making everyone an astronomer. It's just very good in actually showing people the scientific, method of actually approaching things, which, for example, especially during the pandemic, etc., you actually saw how unscientifically most countries, most politicians, most people handle the whole problem. It was very, very unscientifically, and that's when you realize that what's very, very important is we really need to teach people or show people what is the scientific method, how do you actually look for evidence, how do you build your theories, and do things like that. So the purpose, I would say, that now I've kind of evolved from not astronomy as everybody becoming an astronomer, but astronomy more as a tool to show people the scientific method and how could they actually analyze things scientifically and things like that. So I would say that a very important aspect is public outreach, and I see that of late a lot of organizations in India as well as abroad have been taking public outreach very, very seriously, which is very nice. So like I said, we had a planetarium, and the planetarium we had some regular lectures being given by astronomers who from the city on Sundays, on weekends, or on specific occasions. And I think that was also a very important aspect, because you actually, in outreachy things, you just see a lot of nice pictures and it all looks very nice. But if you actually have an astronomer talking to you, he'll show you some, plots and some equations, and you'd be talking real business, which actually probably is a better indicator to you of what doing astronomy is all about. Because again, like I said, often people just see the pretty pictures of James Webb and they think that's what it's all going to be doing. Or even Samuel spoke today about test data. It's all very colorful and very nice, but when it actually gets on to doing science with it, you're actually doing a lot of coding and a lot of things which would appear mundane to people compared to what the glossy, jazzy look that you see in the way astronomy is portrayed. So often when I talk to students, I tell them, there's a lot of physics, there's a lot of maths, lots of computers in it. It's not just beautiful pictures. So that's it. So I mean, that's when I was convinced that I wanted to do astronomy. And at that time in India, we had a lot of very good Russian literature, very good Russian books on astronomy, and I was very strongly attracted to that. I had a lot of my friends who were trying to go to the US, because that seemed the simplest way to go abroad to do astronomy. Especially because in India, most places astronomy was not there as a postgraduate course. You would have had to do it only at PhD level. You would be doing just physics or maths. So the idea was to go abroad so that you can start doing astronomy at an earlier stage. And I was attracted to the idea of going to Russia instead of America, because of all the great Russian books and the literature that I'd seen. And I really saw that the way they approached things was very, very different. And that's how I went to Russia at the age of 17 to Moscow State University to actually study astronomy. And I was there for 7 years. The course had to be done purely in Russian. It was a government scholarship, so the government paid for everything. The only condition was that your course was done only in Russian. So I was the only foreigner in my class of 20 people. I was the only foreigner, and everything was in Russian. And in Russia, the other interesting thing is that all the exams are just vivas. They're just oral exams. You do not sit and write any exam for 3 hours. It's all a conversation. So your teacher will just come and talk to you about something. And most exams are even open book exams. Open to an extent where you can read your question today. If you'd like, you can go home and sleep, have a coffee, use the library, talk to your friends, and come back to your instructor. Even after 2-3 days, you may tell him, I want 2-3 days to look up the thing, and you come back there, and that's when you talk to him, and that's all he needs to assess you. He needn't, So I thought this was a very different approach compared to what is done in India. In India, we see that you need to study a whole lot of things, and you're actually just reproducing what you've read in a bunch of books by not looking at the book. You're just showing your capacity to memorize things. And that's what often, unfortunately, students in India do. They memorize things because that gets them across through exams. Well, the Russian approach was very different, where you actually had to converse about it. You were allowed to look at books, you were allowed to use whatever material you wanted, as long as you could convey your understanding. So I think even that was a very important thing about how they conducted exams. And I think that also is something which one needs to think about our education system, of the way in which we take exams and assess students. After that, I came back to India and I did my PhD in Osmania University. That's a university in the country which is the only university which to date has an astronomy department. Most other universities have a physics department, of which astronomy is just a part of the, it's part of the course. So the department is officially a physics department, but you may, study astronomy. That's like the department I work in even now. It's a physics department. Those students who do PhDs will do it in astronomy, obviously. So I was at Osmania University. We have a small telescope also, 48-inch telescope, which was of the university, and a good astronomy department, which was actually very nice. And that was very good for my basis. After that, I did an Indo-French postdoctoral fellowship, and I did my PhD on star clusters, on studying star formation and star clusters. And then it was interesting that the first postdoctoral offer which I got was actually in a different area, which was galaxies and active galactic nuclei. And I really thought it was also a good idea to change your area. The methods were similar, but the area was different. And I thought that would make my, my knowledge base broader instead of just continuing with the same thing. So from star clusters, then I went on to galaxies, and I worked with Hubble Space Telescope data as well as Chandra data. And this was with groups in France, which is in Paris, as well as in Meudon, in Lyon. And I went there, and this was for 3 years, so we did some work together. That was also very good exposure. After which I came back to the country, and we have something called the Department of Science and Technology, which lets students actually put in proposals. The good part about it is that you are the proposer, you are the PI, so you actually work on a problem which you have conceived yourself. You're not working under somebody. And that was a 3-year project which I did. And that was also very nice because, like I said, for the first time, you are your own, you plan the problem and you do it all yourself. So that was also very good in, in training on how to actually think of your problems yourself without using an advisor or someone like that. Now, another important problem which we have in India as well as globally is jobs in academia. And that's why after I finished my 2 postdocs also, getting a job was difficult. And for 5 years, I actually taught in an engineering college where students were actually being groomed to being engineers. So they were, their approach to learning physics or even astronomy was not very serious because that was one of the mandatory courses they had to do, but that's not exactly what they wanted. So that was also, a slightly difficult this thing where you're actually teaching students who do not want to take the subject so seriously because, they are being groomed to become engineers and not astronomers. And then luckily after 5 years in the engineering college, I finally got a university positions. And so now I'm faculty at a university where now I can do my, my usual astronomy business. I can teach it, I can do research, I can have a group. And that's made me happy. So now I'm happily settled and happy to continue with research as well as a certain amount of outreach and education program. Yeah. And by the way, I'm also co-chair for the Women in Astronomy group of the International Astronomical Union. And therefore, we do a lot of programs specifically to encourage women in astronomy careers because there is clearly a deficit of women in astronomy. And definitely some things have to be done. So what I've been focusing on is training programs for women because I think that a lot of the problem comes of women or others not having good self-esteem or confidence in tackling research problems because they just do not have the skills. And therefore, it's very important to train them in the skills, whether it's coding or whether it's data analysis or whatever is the aspect. So we have already done 3 training programs for women, 5-day programs, where we are, trying to train women to get them into mainstream research and this thing. So thanks a lot, and that's kind of my story.
Thank you, Priya.
Yeah.
Amazing. Amazing life trajectory and inspiring story. Thanks a lot. All right, thanks a lot, everyone, for joining us today. Thanks to all the speakers. Quick reminder for next week, we will move back to our usual Monday meeting, 5 p.m. Pacific time. Next week, we'll talk about how to create a CV and a personal website for your professional use. Yeah, other than that, take care, everyone. If you have any questions, feel free to post it on piazza.com. And see you, everyone.